Yeah, I'm Paul, fourth year fellow, fifth year grad student in applied physics at Berkeley. Like Alan said, I am working with Roger Falcone's group in the physics department there. And I want to just acknowledge a bunch of people, including Roger, before I get started, because inevitably I'll run out of time and not mention their names. In particular, all the work I'm presenting here was done at Lawrence Livermore and is the product of a fairly large collaboration there of experimentalists and theorists, technicians, and laser facility people who are mostly listed there. That's been work as a part of Siegfried Glenzer's group there, who's sort of my technical advisor at Livermore in the NIF program. I also want to acknowledge, in particular, Mike Desjarlais from Sandia National Lab, who is a theorist there that I had the opportunity to meet through the practicum program of the SSGF fellowship. So he's been an ongoing collaborator since I spent the summer there a couple of years ago, as well as our international university collaborators. And of course, SSGF, the program, and the support people for their help and their money. So let me just tell you what I plan to say. The talk's sort of going to be in 4 small chunks. I'll start with 2 introductory bits on kind of what kind of physics are we after? What is this warm dense matter stuff that we're studying? And then how do we study it with X-ray scattering? And then I'll explain briefly 2 experiments that have made up the bulk of my dissertation work using these techniques. Okay, so let me start. Usually these talks start with some version of this slide, which is the temperature density phase space. And you can maybe situate yourself in this image, density on the x-axis, temperature on the y. So if you're a plasma physicist, in a traditional sense, you live in the kind of top left corner where things are very hot and they're not too dense, and temperature matters a lot. If you're a condensed matter person, you live right on the bottom in the middle where things are pretty cold. The field of warm dense matter kind of is right in the middle where things are hot enough that it matters, but cold enough that solid effects matter as well. And you might say, well, why is that interesting? But you see there are some plots of sort of physical regimes of interest here that kind of overlap with this state of matter. In particular, planetary science comes up a lot in this regime. And there have been former fellows, Dylan in particular, that was really interested in that question. And of course, inertial fusion has raised questions in the same physical regime, which is kind of the angle that I come at it from. So yeah, basically this regime is challenging for a few reasons. One is that it involves a lot of the physics of both high temperatures and low temperatures. So you have to sort that out theoretically, which is hard. Also, typically this is studied in dynamic experiments, which means they don't last very long, and it means they're fairly noisy. Energy densities are very high, and the targets are dense, so they're opaque to optical probes. So they're kind of hard to study using a lot of, for example, optical spectroscopic techniques. And of course, you have to make them. So to get targets into these conditions, you have to heat them up somehow. I'll suggest 2 ways of doing that. One is using shock heating, where you compress and heat at the same time. This is, of course, how inertial fusion schemes get the targets very hot. Another way is isochoric heating, where you heat volumetrically, but you don't actually change the density at all. And you can get different physics in these 2 cases. I'll give you an example of each of those. And what we basically do here is use X-ray scattering as a way of getting inside the targets and extracting relatively sophisticated information about the structure of the ions and the electrons in the dense plasma. In particular, I've been looking at how ionization happens in these systems and what that can tell us about the underlying physics. So let me present the technique of X-ray scattering that we use really quickly. It's fairly straightforward. Photon in, photon out, X-ray scatter off electrons. And so if you collect scattered X-rays, you can learn something about what the electrons are doing, which tells you a lot about the physics. So if you have a more or less monochromatic X-ray probe that scatters off the electrons in a dense plasma, and then you put a detector at some well-defined angle, you're looking at a momentum transfer from that scattering process. And that gets inside the physics of the system. In particular, if you look at very large scattering angles, you're probing very short k vectors, or I'm sorry, very long k vectors or very short scale lengths in the system, which means that you're probing individual electron dynamics. So you can study the distribution function of the electrons in that system, for example, which might tell you something about temperature or electron density. And the other limit, in forward scattering, you're probing very long scale lengths in the plasma, which means you're outside of any screening length that is in the system, and you see collective effects. So in particular, I'll show data scattering off plasmon resonances in the system, electron-electron waves, which tells you something about the free electron dynamics in the system, which can give you information about electron density and ionization, which is what I'm interested in. So here's what a hypothetical X-ray scattering spectrum might look like. And we generally, in a cartoonish way, can divide it into three components. One sits at the energy, if you look in the sort of cartoon here, one sits at the energy of the probe X-ray, which is essentially elastic scattering from the ions in the system. And you can write down an equation for what that is. And the important thing to take out of that equation is that the cross-section depends on the ion structure, which is an important descriptor of basically where the ions are, how are they moving. A second component is inelastic. It's scattering off the free electrons in the plasma. And so we call it the free component. It's proportional to the structure of the free electrons, and it typically is sensitive to density, which is an important parameter for the physics that I'm looking at here. There's also a third component, which is scattering off electrons that are bound but that are freed in a Compton scattering event. And that spectrum is actually really closely related to the wave function of the electron in the bound state. So that's a probe of atomic physics in the dense plasma. I'm not focusing on that so much here, but one could do sort of detailed studies of what that looks like under these conditions. Okay, so the system of real sort of interest for a lot of my dissertation work was dense hydrogen. And you might say, why does that matter? Turns out that it's received a lot of attention in the field over decades, more than I had any idea when I started. I probably wouldn't have tackled the problem if I knew how kind of overstudied it was. But there are, in particular, three areas that have, I think, motivated pretty broad research. One is planetary science. So the way that hydrogen acts at high pressure has a lot to do with the structure of giant planets. So what is the conductivity of hydrogen at the pressure equivalent to the core of Jupiter? That tells you a lot about sort of magnetic structure and all these things in Jupiter. Another field I've kind of labeled basic science, but it's actually sort of broad, computational material science. It's just how does the system behave at extreme conditions? It turns out that hydrogen has a really kind of sophisticated phase diagram. There are interesting phase transitions. The one I've shown here is not that clear. I picked it because it's from a recent article published by a former SSGF fellow, Miguel Morales, when he was at the University of Illinois. And it's a hypothesized structural phase transition in hydrogen at high pressure. And that kind of stuff is actually receiving a lot of interest on the computational side. It turns out to be really difficult to study experimentally, and X-rays are a way that you could conceivably look at that. And then, of course, the motivation from the community that I'm coming from, inertial confinement fusion, hydrogen is, of course, a fuel in this system, and how it behaves at high pressure is really important. Okay, that's maybe why it matters. How do you get these targets to the pressure conditions that you want to study the physics? There are a few ways, but the way that I'll be explaining today is using shocks driven by a high-energy laser system. So schematically what happens is that if you shoot a high-intensity laser at a target containing hydrogen, that laser creates a hot plasma at the surface and a very high ablation pressure there, all kinds of mess of particles streaming out from that surface. And it drives a shock into the target. So you have a high pressure shock propagating through the bulk hydrogen, which turns out you can probe, but with an optical probe from the other side to measure what the velocity of the shock is. This is a pretty well-established scheme. It's been done for 20 years, and people have mapped out exactly what happens when you shock hydrogen to high pressures. And the answer is that it turns into a metal. So you squeeze atoms together so close that electrons pop out. So what I'm plotting here is what's called the Hugonio of the shock. It's basically what happens to let's say pressure as a function of density, for example, the trajectory that the material traverses as it's shocked by a single shock. So as the thing gets compressed, pressure goes up. At some high compression, the atoms are close enough together that the electrons are basically forced out into the continuum, and the thing becomes a metal. So that was observed about 10 years ago using this visor technique, which is basically a macroscopic technique. As you can see, there are a bunch of theoretical curves and there are a bunch of experimental curves, and which one is right is actually the subject of a fair bit of disagreement to this day. And we thought, well, it'd be interesting to look at that system, but instead of doing the same thing again, what if we could look actually at those electrons as they are freed in the compression process? So we built an experiment to do that. This happened at the Janus facility. Oh, sorry, at Lawrence Livermore. Just gonna close this. Okay, so Janus is a laser at Livermore. It's a two-beam, we would call long pulse or nanosecond laser facility. And what we did is we basically took a small target containing hydrogen, and with one laser beam, we shocked it to high pressure conditions. And with the second, we created an X-ray source by shooting at a piece of silicon nitride. So you get silicon hot, and it radiates a bunch of lines, including this one at 2 keV. So the idea is with the first pulse, you shock the system, you wait for that shock to develop in the target, and then you probe it with X-ray pulse, maybe 10 or 15 nanoseconds later, and you see what comes out. We also had a visor beam on the end to look at how fast the shock was going to kind of establish our baseline conditions. This is what the target looks like. It's kind of a centimeter or two big. It's made out of copper. It's sort of big because you have to get it cold. Hydrogen liquefies at, or deuterium actually in this case, liquefies at 19 Kelvin. So you fill the center with a little bit of gas, and then you cool the whole thing down to 19 Kelvin. And the drive beam hits the front of it to drive that shock. The source beam hits the side to pump that X-ray source, and then these cones are covering up X-ray exit ports at scattering angles in the forward and backward direction. So the X-rays go in from the side, and then they come out top and bottom and go to spectrometers so we can look at the scattered information. That's kind of what the target looks like lying on the desk. It has been sort of the bane of many hours of assembly at 3 a.m. So as you cool the target, you can also see the gas bubbling out and the liquid forming in the target at 19 K. So that's kind of a fuzzy picture of that. Okay, so you do the experiment and you get an X-ray spectrum out. What do you see? Well, starting on the left, which is data from our forward scattering experiment, looking for plasmon oscillations, the results are actually kind of interesting. If you compress the system to not quite 3 times, you see one sharp peak on the bottom here, which is that elastic scattering feature that I explained before. So you're scattering from the ions in the system, but there's no signature from free electrons, which is to say there's been no ionization at all in the system yet. If you increase compression slightly, however, this feature appears to the red of that elastic feature, which is a plasmon signature. So this is basically what happens when you scatter off electrons, free electrons in the system, just bouncing around against each other at a characteristic frequency that you can relate back to an electron density. So that's basically a measure of free electron density, and we can fit it with a code that calculates this stuff. If you then look in the forward direction, or I'm sorry, in the backward direction, where you're essentially seeing Compton scattering, you can kind of confirm that result with another electron density measurement. to sort of as a sort of sanity check that what you see is in fact free electrons. And this is also kind of helps us nail down the temperature in the system and know that we're looking at something real. Okay, so on the left is the velocity history of the target for that first piece of data that I showed, which basically tells us what the pressure in the system is. And if you put all of this together, these X-ray spectra and this velocity history, you can basically make a plot of the ionization of this compressed hydrogen as a function of its compression. And what you see is actually kind of neat. There's a really sharp onset. This is actually a log plot. So there's a really sharp onset of ionization right around compression of 3 times in the system, where all of these electrons become free kind of all at once, and the thing just ramps up on its way to becoming a metal. There are also a bunch of other lines on this plot, which are kind of preliminary theoretical calculations, and I would point out that most of them are very wrong. So this is an interesting plot because it sort of says, okay, now we can kind of microscopically look at what the electrons are doing. Rather than in a macroscopic, this is what a shock is doing kind of way, we can say, oh, this is actually where the electrons are beginning to become free. Is there a way to calculate this? And so far the answer is there's no great way to calculate it, although Mike at Sendia and I have been talking back and forth about maybe thinking of a new way to do molecular dynamic simulations to really understand what's going on that slope. So that is a work in progress, but compressed deuterium there. Okay, so on to a second experiment. So now forget about shocks and forget about hydrogen. This is totally different, but the diagnostic method is the same. So there is an effect in laser matter interaction called TNSA, which stands for, I think, target normal sheath acceleration, which is basically this effect where if you shoot a high intensity laser at a solid, especially a metal, and if it's thin enough, you get all kinds of high energy particles off the backside. So the physics is kind of complicated, but the idea is if you have a laser that's sort of up at least around 10 to the 18 watts per square centimeter incident on a target, you drive a bunch of electrons, hot electrons, through that target, which creates a really high gradient field on the back surface of it and pulls all these protons off. So at the end of the day, you get a relatively high energy, a relatively high efficiency proton source. Why does that matter? Well, it turns out you can use that proton source to heat a second target to these warm dense conditions that we're interested in. So we built an experiment to do this, and again to study what was happening with ionization in this system. And the important difference here is that whereas before we were looking at essentially pressure effects, what happens to electrons when they're kind of squeezed close together, now we can throw away all the pressure stuff and just isolate what effect does higher temperature have on these systems. So there we go. This is what the experiment looked like. So just on the left side, you can sort of see in a 3D picture 2 laser beams. These actually came from one laser system, the Titan laser at Livermore, which is the high intensity system there, which we split into 2 so we could sort of sensitively co-time them. With the one here labeled proton drive, we focused it to a high intensity to create that proton beam I was talking about. With the second one, we focused it on a second foil to create a K-alpha X-ray line, which is a sort of short-lived X-ray radiation source. These are both kind of 10 picosecond beams. And then both of these, the protons and the X-rays, were pointed at this target, for which we used boron or boron nitride. So the idea is that the first pulse in time hits the protons and gets the target hot. The second pulse hits the X-rays and probes the target. The X-rays then scatter out, they're spectrally dispersed, and we can investigate what's going on. Okay, so this is sort of a little bit of data showing what we see. So on the left, I've plotted just the spectrum of the protons that come out of that interaction. They're sort of on the order of 5 MeV, and with kind of a long tail. What that basically means is that almost all of their energy is deposited in the first sort of 50 microns of the target. So you get you can do hydrodynamic simulations, and you can see that that target, the first layer gets to between 10 and 20 eV. It's kind of around 16 eV, and we tried to measure the temperature with X-ray scattering and sort of confirmed those simulations. So you basically have a target which is sitting at around 15 eV, which should be acting pretty much like a plasma at these conditions. It's fairly hot. And then we do, again, X-ray scattering and get spectra that look similar. But here I'm showing different results on the left and right. Left is boron, the right is boron nitride. Otherwise, everything is the same. So the temperature is the same, all the experimental parameters are the same, the scattering angle is the same. On the left, so I show cold scattering, where again you see that characteristic elastic scattering and no other features. When you get the thing hot, you see again this plasmon thing. So free electrons shaking around in the system, which you can fit to an ionization of degree of like roughly 3, which is what any kind of plasma physics model will predict. If you take exactly the same physics, you just put in a boron nitride target instead of a boron target, what you see is totally different. There's no plasmon resonance. There's a little bump, which you can kind of set an upper bound of less than an ionization degree of 2. It's probably closer to 1. It's kind of in the noise, so you can't fit it very well. But this is actually a little bit of a puzzle. So from a simple plasma physics perspective, these kind of targets at similar temperatures should be acting almost exactly the same. So why are they not? We didn't know, so we asked a theorist. And he gave us these really messy plots. I have to apologize for those. But basically what he did is he simulated these systems using 2 models. One is something called Purgatorio, which is kind of a standard plasma physics computational package. And one is something called MECA, which is like a condensed matter package. And the idea is that by comparing them, hopefully we can get a sense of what's going on in the physics. So I would encourage you to ignore like all the squiggles in the plots and read the yellow boxes. So I'm showing boron here, which is the one that acted sort of as we would expect. So boron in a ground state is a semi-metal. And when you get it hot, it turns into a metal pretty easily. And that is what both of these codes predicted. And the ionizations that they predict are both within the error bars of our experiment. So you get it hot, the electrons sort of pop into the conduction band pretty much exactly as you would expect. So no surprise there. When you look at boron nitride, things are a lot different. The ground state of boron nitride is an insulating state. And it has a fairly wide band gap. And when you get it hot, a plasma physics code, which is this ugly red line, is predicting a similar result to boron. So you should see an ionization of about 3 because everything's hot and there's no real band structure in a plasma. But the condensed matter code actually sees the existence of band gaps at this high temperature still. So there's some kind of liquid band gap in this system. And what that means is that the electrons are still not hot enough for most of them to jump into the conduction band. So this predicts like a rough agreement with our measured low ionization in that system. And this is interesting and surprising. As far as I know, nobody's ever seen sort of condensed matter effects like this at temperatures this high in equilibrium systems, at least. So in femtosecond level systems where just electrons move, you can imagine that being the case. But in this system, which sort of evolved over picoseconds as in thermal equilibrium, this is kind of a new result. And to be honest, I don't have like complete 100% confidence in this code. It's still under development at Livermore, and obviously it looks sort of messy. But we're working with theorists using other models to hopefully confirm what this is predicting. But so far, this is looking more and more robust. So it seems that we've measured sort of an important kind of band structure effect in relatively high temperature plasmas. So I am pretty much out of time. But let me just conclude by reminding you of the D2 and proton-heated experiments using X-ray scattering as kind of a new method to understand electron structure in warm dense matter. So thank you.